Hi all. So I'm coming to the end of my first year of my PhD at the University of Cambridge, and I think you'll agree we've seen a lot over the last day or so about the importance of sulphur and controlling the sort of trace element budgets of magmas and how that's important in terms of sulphur degassing at lower pressures and sulphide saturation at high pressures. But despite this kind of importance, we still know surprisingly little about the solubility of sulphur in these magmas. Of course, that's important for thinking in terms of crustal differentiation, mantle evolution and planetary chemistry and associated processes. But to really look at this sort of interplay between sulphide saturation and at low pressure and at high pressure and sulphur degassing at low pressure, we've been examining some oceanic plateau basalts where you're relatively free from a sort of continental contamination influence, and you have sort of voluminous eruptions of basalt on the sea floor to really look at how these processes work in these systems. And we've also been we've been doing that with laser ablation IPMS on glasses so you can get good liquid lines of descent. And we've also been looking at sort of Chalcogen variations, ratios and absolute values so that we can begin to resolve sort of other chalcogens, so selenium for instance, perhaps use these to reconstruct sulphur concentrations prior to sulphur degassing. So just before I get into the sort of main body of the talk, I just wanted to highlight the two sort of key processes that are important for the rest of the talk. Of course you have sort of high pressure sulphide saturation. This is the Morb array, so as John was talking earlier about the Morb glasses, you have saturation in the sulphide phase and then we're depleting, so copper on the y-axis, and as we differentiate, we're getting rid of copper, essentially sequestering copper from the melt. And these ones with slightly higher copper are just plume proximal arrays, but the typical Morb you see were saturated in sulphide. And this is obviously governed by the solubility of sulphur in the magma and has of course a significant influence on chalk-file elements. And then at lower pressures where we see sulphur degassing, this is just the data collected by SIMS for our glasses for oceanic plateau basalts, but I really just wanted to show this graph, it doesn't matter for the moment, that where we see degassing, we've got differentiation and then we see sudden degassing of sulphur. And that sort of decompression where we have eruption at lower levels. And of course this is important for what Emma just showed with sort of melt vapour partitioning. So the three oceanic plateau basalts that we've studied are the Shatsky rise off the coast of Japan, the oldest one, about 140 million years. And then we have Ongtong Java, which is the largest by size, perhaps the largest outpourings of basalt seen on the Earth. And of course, Kerguelen in the South Indian Ocean, which is the smallest by volume. And these cover a range of approximately 5 to 10 weight% magnesium in terms of how differentiated they are. And I just wanted to highlight these coloured units at the bottom of the individual boxes for each plateau. These are the sort of subunits or massifs for which we have measurements and data for, so the sort of best resolution we can resolve to for each of the plateaus. So these colours will be in the graphs throughout the talk, just to keep note of that. So in terms of sulphur, the bulk glass sulphur contents that we see, which was measured by SIMS, we have sort of incompatible behaviour in the bulk of the samples. So in both the Ongtong Java, the Kerguelen in the red, and the Shatsky rise in the purple, in the green here. But what we do see is we see the Tamu massif, so the purple, which is part of the Shatsky rise, we see degassing behaviour. So we have relatively flat plateau here at the start at roughly about 800 ppm, which perhaps an olivine control line before we have other phases in the liquidus and we start to ramp up the sulphur a bit more. So I first look at evidence to see if there's any sulphide saturation in these samples. So we look at copper as kind of a sort of first order indicator of sulphide saturation. Of course, copper is chalk-file, it has a D into sulphide liquid between about 900 and 1100. And what you can see is that copper, taking the group as a whole, copper kind of ramps up fairly quickly. We're at 10 weight % MgO in the most primitive Krenke basalts. We have about 100 ppm, so fairly standard compositions for a mantle melt. And this increases up to around 350 ppm. We see no direct evidence, sort of, as we see in the Morb array, for sulphide saturation in terms of chalcophile element, trace element abundances. And of course we know the morb is sulfide saturated because when we look petrographic evidence, you can see little sulfide blebs and morb glasses erupted on the sea floor. But if we look slightly closer, you notice that taking the Ongtong Java, so the yellow, the orange and the blue, we can see that there is perhaps a slightly shallower increase in copper. And at a given MgO content, we're actually at higher copper contents in the Kerguelen, the red, than we are at the most that's sort of similarly differentiated Ongtong Java basalt. So we see that there is a difference in the chalcophile element abundances. So to really sort of deconvolve this further, we've looked to model the sulfur content at sulfide saturation, and we've been using the model most recently published by Dwayne Smythe, part of Bernie Wood's group at Oxford. And he presented a really nice model based on experimental work, where he also took into account the composition of the sulfide phase. So what we've done is we've taken our glass measurements and we've modelled the sulfur content at sulfide saturation as a function of pressure, temperature, and the composition of a hypothetical sulfide phase that would saturate in these melts. And we've just taken a typical morb sulfide composition. So this is plotted up not against magnesium, but as total iron in the melts. And what I hope you can see is that this is the sulfur content at sulfide saturation, these dashed lines. And this is actually our measured sulfur values for the morb array here in grey and our plateau basalts in the coloured diamonds. So this is for a 1150 degrees sulfur content at sulfide saturation. And these are pressures in GPa, so 0.1, 0.51 and 1.5. And what I hope you can notice is that we are sulfide saturated in the morb, and we actually follow one of these arrays very nicely with in the morb sulfur contents at a pressure which is reasonable for a sort of beneath the oceanic crust in a sort of magma chamber at mid-ocean ridges. But what we also see is that although you wouldn't expect the oceanic plateau basalts to be sulfide saturated, we do actually follow one of these sort of isobaric lines of constant pressure, which we could then perhaps suggest that if we had no sulfur, sulfur was behaving completely incompatibly and not being sequestered by any phase, we might expect the sulfur to ramp up at a steeper gradient. And if sulfur was degassing, it would be coming along this way. So something appears to be sort of buffering the sulfur contents of these melts, which I suggest based on this is in fact sulfide, even though in terms of copper and chalcophile elements, we don't see this sulfide expressed, which is perhaps just because we don't have enough sulfide to actually make the bulk distribution coefficient of the copper compatible. So this simply then can be explained by the fact that because we have higher, thicker oceanic crust, we're actually at higher pressure, so that if we have higher pressure sulfur content at sulfide saturation for this given temperature, we actually can begin to follow this array of sulfur in the oceanic plateaus very nicely. But in terms of the thickness of each arrays, and then particularly in the morb array, what controls this variability, not just in the gradient of the line, but also the sort of variance in the data? Now that can be explained quite easily by if we take different temperatures. So we know morb magma chambers are replenishing systems from trace element work and various papers over the years. So we can then just plot up for a reasonable pressure for the morb array. So for mid-ocean ridden magma chambers, we've got 0.1 GPa, say. And then we just have two different temperature lines, which the morb array fits in very nicely. So you can imagine an intrusion of magma into this magma chamber. You have you've got sulfide saturation, it begins to cool. And then you've got a sudden influx of fresh magma, so you're bringing the temperature up again. So we're continually varying at sulfide saturation between these two lines. So to a lower pressure now, to look at degassing, we've used a carbon dioxide and water sort of model to model eruption pressures and then therefore eruption depths based on the carbon dioxide and water content of the melt. So this is just the carbon dioxide contents of the glasses measured by SIMS and as a function of magnesium. And perhaps we have a small bit of differentiation in these Ongtong samples from the most primitive to these sort of intermediately differentiated Coimbatore samples. But the bulk of the samples are all degassed in carbon dioxide. But if we take this maximum concentration of carbon dioxide, we can actually model that as a pressure of 0.42 kilobars, which corresponds to a depth of approximately 3,000 meters. And then when we plot CO2 against these calculated depths, so this is based on the volatile calc model, well used, Newman and Lowenstern, and in the basalt water carbon dioxide system, we can see that we, of course this is modelled, we follow very nicely, so we can, the carbon dioxide content of the melts is a function of the depth in the ocean at which they were erupted. And these ones that appear as sort of high pressure degassing is where we have sort of anomalous water contents. So if we plot this eruption depth up against our sulfur data, it does fit quite nicely then that the sulfur degassed Tamu Massif samples from the Shatsky Rise of Japan are in fact part of the lowest erupted samples relatively. And you see these ones slightly higher yet undegassed, and that is because this graph obviously doesn't take into account how differentiated the melts are. So these purple ones are actually in fact the most differentiated samples and degassing sulfur at a shallow level, whereas these ones are not. And this fits with fossil data as well, so people look at fossil assemblages and they see at what depth they were likely erupted based on where the fossils or the fauna lived at the time. But this sort of leads on naturally to then say, well, if we had degassing of sulfur, how much sulfur were we basically getting rid of out the system? So it's very difficult sort of where we have degassing to follow the sort of how much sulfur was in the system before it was degassed. And one of the things you can do if you have an array of sulfur data is of course just plot a line through it all and backtrack to that line for a given MgO content. But if you don't have that data, if you don't have access to SIMS or things like that, it's difficult to measure sulfur. So we've been measuring selenium. Of course, anybody that knows mass spectrometry, groups 15 and 16 of the periodic table are notoriously difficult to measure. They have isobaric interference, polyatomic interferences. But what we did is we measured selenium with an oxygen reaction cell with the laser ablation. So you can see that selenium behaves similar to sulfur in terms of its bulk distribution coefficient with decreasing MgO. But for the Tamu Massif, which you'll remember was degassing sulfur, it doesn't degas in selenium. So if we then have well-constrained Chalcogen ratios, sort of sulfur-selenium ratios, we can actually back-calculate sulfur contents with a reasonable accuracy. And sulfur-selenium, because of the different bulk distribution coefficients, increases slightly. So there is a slight gradient on this line, and we see this better in the Marbury. But this is just the data for the oceanic plateaus. And you can see because of the degas sulfur, we're down here in the Tamu Massif. But we can take a sort of average around this point for the Tamu Massif and the Shatsky Rise, and then just plug in the numbers. And then we can back calculate sulfur star, which is essentially sulfur content prior to degassing. And you get a sulfur content of around 1200 ppm, not degrees, sorry, which represents about 68% degassing of sulfur in the Tamu Massif. And you can just plug in some numbers. So if you assume that's all SO2, if you assume a sort of relative melt density of 2.5 grams per cubic centimetre, you can actually just work out that the Tamu Massif during eruption, and of course a reasonable volume of basalt for the Tamu Massif, about 1.2 times 10 to the 13 tonnes of sulfur dioxide. What time have we got? So just to finish up on this, we have the amount of sulfur that was erupted in the Tamu Massif. We can calculate the depth of eruption based on the CO2 and the water data, and we can calculate the present day level that these sit at based on just simple bathymetry in geophysics. So we can calculate subsidence by just obviously taking away the present day bathymetry from our modelled CO2 data, which of course has a lot of error in it. So these are more just of a relative exercise as opposed to absolute value depths. But what you can see and what you'd kind of expect is that the biggest plateaus, the Ongtong Java, so this is estimated volume along the bottom, have subsided the most. But what's important here is that there is no apparent degassing from our data, certainly in the Ongtong or the Kerguelen, but we do see it in the Shatsky, so the Tamu Massif, the purple diamonds that we looked at, and we have this amount of sulfur dioxide coming off. But this just goes to show that plateau size / volume is not really a reliable indicator of how much sulfur, or as sulfur dioxide or another species, was released as a volatile during eruption. So, and obviously this is important for people who consider things like mass extinctions and atmospheric sort of things to consider. So that's just my conclusions, but I'll just highlight the two main conclusions. Is that what we see in these oceanic plateau basalts is that although we don't typically think of in terms of a sort of these two binary, we have sulfide undersaturated or sulfide saturated, we would typically assign these oceanic plateau basalts as sulfide undersaturated because of their chalcophile element systematics. But what we appear to have is this sort of cryptic, almost sulfide buffer that's buffering the sulfur contents, and we can see that when we plot it up relative to its sulfur content at sulfide saturation. And of course, what I just finished up on there is that plateau volume and size isn't really a reliable indicator of how much sulfur we degas. So we have to bring in considerations based on eruption depth and obviously how differentiated the melt is. So thanks very much.
Any questions for Callum?
I was just a bit intrigued by that point number 3 there. When you look at copper increases during differentiation, so the D's really pretty low.
Yes, yeah, the bulk D.
But you told us that the D of sulfide is about 1,000.
Yep.
But you're sulfide saturated.
Yep.
And you said the D is very small because you've got very little sulfide crystallizing. Have you checked that calculation? You've got a D of 1,000.
Yep.
So and you've got to multiply by so little sulfur, so little sulfide to get that value down being really small. Mm-hmm. I just did the back of the envelope calculation. I don't think you can make that work, but maybe you've tried.
Yeah, so no, I totally agree with you there that you need sort of vanishingly small amounts of sulfide, which might not work in terms of even buffering the sulfur, if that's even possible. I would have to, that's one of the things I have to look at in more detail, is that bulk, and to see if it works. Just in terms of what I've been thinking of it as at the moment is that you sort of, you're obviously the amount of sulfide you get at sulfide saturation is going to be based on, related to your sort of overpressure of sulfur. So how much sulfur content is over and above your content at sulfide saturation. So it must be the case that the sulfur content in the oceanic plateaus is kind of wavering around that sulfide content at sulfide saturation. So you perhaps are only getting vanishingly small amounts of sulfide, but I agree that the maths is pretty hard to fit into that model at the moment, certainly, before we look at it further.
Yeah, so you're calling these things oceanic plateau basalts. Are you distinguishing them from continental flood basalts, from large igneous provinces, from oibs? Could you just clarify what you mean by that? Is this supposed to be a plume thing and it's coming from some significant depth?
Yeah, well, if you actually look at the sort of literature on this stuff, there's even sort of a discussion as to whether Ongtong Java is plume related or not. I mean, people are in favour of, there's one paper out there that relates this to perhaps an impact and then massive melting related to the impact in Ongtong region. And certainly Kerguelen, there's arguments that perhaps, not Kerguelen, Shatsky, there's arguments that there isn't even a sort of plume there at all to feed this magmatism. Perhaps it's related to some sort of rift-related tectonics, obviously being so close to Japan. But I am distinguishing these from things like ocean island basalts, so places like Iceland, where we're not near, at these certainly not near mid-ocean ridges. We're impinging on oceanic lithosphere, which we could probably argue was about 7 to 10 kilometres thick, maybe slightly more when these things erupted. No, There is perhaps, if you look a bit deeper into the literature, arguments for there being a continental influence. Certainly Kerguelen, a historic continental fragment based on some isotopic and geochemical data. But for the moment, we're just treating these as simply a plume-fed magmatism onto oceanic lithosphere, erupted submarine with very small amounts of magma, possibly erupted subaerially based on some petrographic textures. But I am distinguishing them from places like continental flood basalts, so like Norilsk in Russia and places like that, where you have massive base metal sulfide deposits. But of course, to get the sulfur there, you always need to explain it with an addition of a sort of reducing agent, so sort of organic rich seals. So here we obviously have none of that.
So could you just show us the thing where you had the Morb array and pressure contours, and then your little red spots there?
Yeah, that one.
Yeah, so I didn't get your explanation for why we're sitting sort of outboard. Is that 15 kilobars there?
That's 0.1, 0.51, and 1.5 GPa, not kilobars. Yep.
So what's your explanation for why they're sitting out there and why they're sort of following this pressure contour?
So these isobaric lines are the sulfur content at the modelled sulfur content at sulfide saturation. So as we are sort of differentiating, so increasing in iron and wrapping up the sulfur contents as an incompatible element, so at high pressure without any degassing, based on the composition of these melts, we would expect that when we hit this line, sulfide begins to, an immiscible sulfide phase forms. And then we follow this line based on the fact that the sulfur content is going to be buffered along this line, because that is the model sulfur content is sulfide saturation for this pressure. Does that make sense?
Yeah, okay, so the idea here is that it has the appropriate amount of sulfur in it for a high pressure melt. And
Yeah.
it stayed undersaturated because it was decompressing.
The Morbury is sulfide saturated. So that it is sulfide saturated because it follows one of these, it hits one of these lines.
Right, well, the Morb is, but yours aren't, are they?
No, so you could fit a line if you go to higher pressure, but the relative error in Duane's model is between sort of 300 to 400 ppm. So there is variance in the y-axis on these lines. It's not a sort of perfectly constrained model at the moment.
But your conclusion based on this is that it's from a significantly deeper source than Morb.
Yeah, so it's evolved deeper at higher pressure, which is why the sulfur content isn't higher, because we're at higher pressure, which explains why perhaps we do have this sort of cryptic sulfide saturation buffering the sulfur contents at higher pressure.
So your melts are imaging restite sulfur in the region that they departed from. That sulfide saturation control is the restite sulfur in the mantled source region from which the melts departed. That's your sulfide control. At 20 kilobars.
Yep.
2 GPa.
You mean down here? Yep.
That whole, your colored symbol array.
Yep.
The sulfide saturation.
That's different. We have to be away from the mantle source here. That's differentiating. So these aren't melts. These are related cogenetically by differentiation. Certainly, we know the blue and the orange are. So that's differentiation in a magma chamber ascended away from the mantle. It's sort of perhaps the mantle crust boundary. It can't be a control by sulfide restites in the mantle source. I don't think.
Cut that off there, and you guys are welcome to ask Callum more questions while we let everyone get some tea and coffee. Let's thank all of you again.